Hey folks, welcome back. We're now at part 2 of lecture 7.1, talking about changes of state. And we left off talking about the energy transfer involved in every phase change. And so now we can think about whether energy is absorbed or released. And we have names for that, right? Endothermic and exothermic. And so we're going to apply these to the different phase changes. So when heat is absorbed from the surroundings, that means we're going up in energy of the substance, right? So that would be going from solid to liquid, or liquid to gas, or solid to a gas. When heat is released to the surroundings, then the resulting substance has lower temperature, lower energy. So freezing, right? Going from a liquid to a solid, or going from a gas to a liquid in condensation, or from a gas to a solid in deposition. So here's the words, and I want to go back to a visual because sometimes having both of those side by side is helpful. So we saw this before, and now we can add some new terms, or old terms really, but if energy is added, meaning we go up in this chart, it's an endothermic process, right? Heat has to be absorbed in order for this to occur. And if we're going down, energy removed, it's exothermic. Heat is released. Right, so we see again melting, vaporization, sublimation are endothermic physical processes, and freezing, condensation, deposition are exothermic. Heat is released. Where? To the surroundings, right? All right, let's spend a little bit more time talking about melting and boiling points and defining them. These are the kinds of things that we have some familiarity with, but for any substance, you could look these up in a table because they've been experimentally determined, and it's considered as measured at normal atmospheric pressure, so it's sea level, and it's like, what is the temperature at which boiling point a substance undergoes phase change to gas, or a melting point, temperature at which a substance undergoes solid to liquid. So, right, notice that these are temperatures. So boiling is a process from liquid to gas. Boiling point is a temperature value. So like for water, for example, it's 100 degrees Celsius. Melting point, again, is a temperature. So the melting is a process, melting point is a temperature. And just to point out that the melting point is identical to the freezing point, right? Same temperature. Liquid freezes at the same temperature that the solid melts, and the boiling point is the same as the condensation point. It just depends on which way you're thinking about it, or which way you're going. All right, we're finally to the point where we can show a heating curve. So a heating curve shows a lot of information in one little plot. It shows how the temperature of a substance increases or remains constant as heat energy is added. So we see across the x-axis heat added, and across the y-axis is the actual temperature measured of the substance. Something strange happens when we see these horizontal lines, which means heat is still being added to the substance, but the temperature is not going up. So what's happening at those places? Well, those places are phase changes, and I'll explain more about that in a moment. But first we can see, if we start down at the left corner, we have the lowest temperature, and as heat is added, we see that the temperature just goes up linearly up until a point at which it stops increasing. Heat is still added. Phase change, the melting occurs. Then we continue heating. Actually, you know what? I'm going to go here. This walks through each step. So we have a solid. It's being heated. Added heat causes the solid particles to increase in kinetic energy. Therefore, we see a rise in temperature, right? And then we get melting. This is the strange part. I want to spend some time here. All of the added heat causes some of the intermolecular forces of attraction to be disrupted, resulting in a phase change. So the heat is being added, it's being used to do something, but it's not being used to increase the kinetic energy and increase the temperature, right? There's no change in kinetic energy, so the temperature does not rise. This is also known as the heat of fusion. So how much heat needs to be added in order to melt is called the heat of fusion. So after this now, when we're like within a phase, now as heat is added, it causes the liquid particles to increase in kinetic energy and temperature goes up. Then we have a similar thing happen again. We have a flat spot, and that's the next phase change, right? Flat spots are phase changes. So here, the heat is still being added. It causes the remaining intermolecular forces of attraction to be disrupted, resulting in the phase change from liquid to gas. This is called the heat of vaporization. But again, that heat energy being added is going towards disrupting intermolecular forces of attraction. It's not changing the kinetic energy. There's no temperature change. And then we see now we just have a gas, and as heat is added, the temperature goes up. The top part of the figure shows on the particle particulate scale what's happening. Right, so in A, we have just solids kind of well lined up. B, the phase change is occurring and it's starting to disrupt intermolecular forces of attraction. Then we have a liquid. Then we have a phase change again, and that will continue without any temperature increase until finally all the intermolecular forces of attraction have been disrupted and you have a gas. So a few important points on there are the heat of vaporization and the heat of fusion. So just to make this explicit, let's define these and also give them the symbol delta H, right, which is the change in energy, the heat required. So the heat of fusion is the amount of energy required to melt a solid at its melting point, at the temperature at which it melts. And the amount of energy required to freeze a liquid, this is the same amount that you would have to remove to freeze. So again, these processes you can go reversible, right? All right, the heat of vaporization is then just the amount of energy required to boil a liquid at its boiling point, or the amount of energy needed to be removed to condense a gas. These are the kinds of values that you may look up, on a table or something. They would have units of something like calories per gram, or joules per gram, or joules per kilojoules per mole, something like that. So let's see what this means. This is heat, so the amount of heat required, but then it's divided by how much of the substance you have, right? So if you had 10 grams of a substance, it would take a certain amount of heat to melt it. Now, instead of 10 grams, if you had 20 grams of the same substance, it would take twice as much heat. But the heat of fusion itself is basically scaled down by grams, or sometimes by moles, which is similar to grams. Turns out that the delta H heat of vaporization is always greater than the heat of fusion, because ultimately vaporization requires the disruption of all of the intermolecular forces of attraction, and it just takes more energy to do that. So delta H vap is always greater than delta H fusion. Okay, so back to the plot for a moment of the heating curve. So we've kind of covered the flat parts. These are the actual phase changes. Now, what influences or what describes the curved lines? Well, this is called the specific heat. This is the amount of heat added or removed from a substance that results in a change of temperature. The definition is the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius. So remember, before, when there was no phase change, we had calories per gram, right? But now we want to know the calories needed per gram of substance to change the temperature by 1 degree Celsius. So that's the unit. It's kind of a complicated unit, but it's calories per gram degree C. That's how we say it. And this is the curve lines, or the linear slope lines within a phase. So a specific heat value would be for a solid. The specific heat value for the liquid and for the gas of a same substance might be different. Okay, and so those are all values that you would need to know in order to understand more about the substance. So if we wanted to say, like, okay, how much heat is actually required to get this change to occur, what do we do? Well, here we use the heat equation. And we see it right here. It's the specific heat times the mass times the change in temperature. And notice that we have calories per gram degree C. And if we multiply that by mass, that would have grams. Temperature, that'd be degrees C. And so what's left is just calories, right? Which is what we're interested in. So if we know the specific heat of a substance, we know the mass that we have, the temperature change that occurs, we can determine how many calories or how much heat was needed. All right, let's power through because I basically have one final example. It's kind of a long one, but it hits all the parts in, and then we'll be done. So this is worked exercise 7.5. It asks, how much heat is required to raise the temperature of 10 grams of ice from negative 5 degrees Celsius to steam at 105 degrees Celsius? Okay, this is the longest type problem you may ever get for this type of question, because it involves all 5 regions of the heating curve. So we have negative 5 degree ice. So first we need to heat the ice from negative 5 up to 0. Why to 0? Because that's where the phase change occurs. So then we need to melt the ice at 0. And now we have liquid water, which we need to heat from 0 to 100, because that's the boiling point when it switches to gas. We need to vaporize the water at 100, and then heat the steam from 100 to 105. So each of these steps we could take one at a time and then add them together for the total heat. Okay, so you might get some part of this question, right? You might get like simply heating up water, and then we would just use this part. and we would actually take the true temperature change. Or we might get something like, just from ice to heating water. So we'd have some subsection of this. So you can see how this question goes all the way from ice to solid to gas. So let's take these steps one at a time. Step 1, heating the ice from -5 to 0. Okay, so we're going to use the equation specific heat times the mass times delta T. All right, and so if you were to look up the specific heat of water solid, we get 0.490 calories per gram degree C. The question says we have 10 grams. It's a 5-degree temperature change, and so that would require 24.5 calories. Now we need to melt the ice. And that's not, there's no temperature change, right? It's just we're using the heat of fusion. And so this is simply the mass, let's be consistent here, mass times delta H fusion. And so for water, delta H of fusion is 75.9 calories per gram times 10 grams. The melting process would be 795 calories. All right, now we have water. We need to heat it up. And we're going to go all the way from 0 to 100. So we have a 100-degree temperature change. We have specific heat times the mass times the change in temperature. And now we're talking about water liquid, which actually has a different specific heat. It's 1.00. That's actually the definition of a calorie, the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So if we have 10 grams times 1 times 100 degrees Celsius, that gives us 1,000 calories. And so, or 1 kilocal, but we'll go with 1,000 calories. Okay, now we need to boil or evaporate the water. So we take the mass times delta H of vaporization, which for water is 539 calories per gram, times how many grams we have would be 5,390 calories. Okay, we're almost done, folks. One more step, right? Now we have gas. We're going to heat that gas. So we're in the final step of the heating curve. Take the specific heat for the solid times the mass times delta T. So for solid, I'm sorry, gas, I said solid. Earlier I meant gas. It's 0.497 calories per gram degree C. And 10 grams, 5-degree temperature change. And so it's 24.9 calories to heat the steam that lasts 5 degrees. So we take our answers, add them all up, and we get 7,234 calories, or you could say 7.23 kilocalories. All right, you'll notice that heating the ice and the steam do not actually contribute very much to the total here. The majority is actually vaporizing. But anyway, there's our answer. So like I said, this is the longest problem you can get because these are the only phases, right? You might get some portion of this, but once you've seen it all together, hopefully that helps. All right, so it looks like we're going to get section 7.1 done in just these 2 videos here, and we'll wrap this one up and come back for section 2, and we'll talk about properties of gases and the gas laws. See you then.